Hello all. A central concept for this week's course of studies has been significance testing. And I know that significance testing is a very confusing set of concepts. And I suspect you're asking the question, so what's the deal? This short presentation is designed to help you better understand, so what is the deal with significance testing? I know at first glance, all of this is very confusing. You have these terms thrown around like parametric versus non-parametric. We're talking about means, or are we looking at proportions and ratios? We're trying to keep track of population versus sample statistics. They keep throwing these Greek letters out there as symbols for ideas, for concepts. And then there seems to be these zillions of different tests that we're supposed to figure out how to do and how to apply. The z-test, the t-test, the f-test, and how about this chi-square thing? And then on top of that, you were asked to look at all sorts of complex formulas. I suspect many of you are like this guy on this box going, I have more questions than answers. Help me, help me, help me. That's what I'm here to do. Let's start with the two terms, parametric and non-parametric. Actually, these are just two words that describe the kind of data that you're working with. So for example, parametric, it's data that's been measured via interval or ratio scale data, known as scale data in SPSS. Para is simply the Greek word for from. So this is data that's from metric sources. Non-parametric data, that's data that's been measured via nominal or ordinal scales, therefore not from metric source data. That helps, doesn't it? Now, can we use scaled variables in non-scaled ways? Most certainly we can. Think about the fact that you can take interval or ratio data, and rather than using the means, you can use proportions. For example, perhaps I've measured age in an appropriately ratio scale, because after all, age has a 0, and each one of the intervals between each age number is equally distributed. But perhaps I want to look at a proportion of those cases whose age is greater than 25 versus those whose age is less than or equal to 25. Now I've taken scale data, it could have even been measured in a scale way, and I'm changing the way that we're looking at the data to turn it into a proportion. Once I do that, then I stop using parametric measures for testing. I will use non-parametric measures for testing. By the way, parametric testing is usually not the default. In fact, non-parametric testing is usually the default. And that's because of some other reasons for using non-parametric testing. First, parametric testing has very specific assumptions. There has to be a large sample size with at least 20 cases, sample size equal 20. The data has to pretty much follow a normal distribution. And when those two assumptions can't be satisfied, then you switch over to non-parametric testing. And non-parametric testing is a little bit more flexible when assumptions aren't satisfied. We've covered the difference between parametric and non-parametric testing. Now let's talk about the difference between using a mean for your significance testing versus using proportions for your significance testing. This is dependent on the scaling of the variable, which shouldn't surprise you. And the scaling of the variable that you're seeking to test, remember that's determined by the inherent nature of the phenomena that's being measured. For instance, age is ratio data because it has a natural 0 and the spaces between the choices, the intervals between the choices are equal. So given that, a mean is a relevant measure of what we call central tendency for an interval or a ratio scale data. But take, for instance, the idea of gender, the phenomena of gender. There's no absolute zero. There's not an equal distance between the choices, and there's no inherent hierarchy of value in the choices. So you wouldn't use a mean as the expression of central tendency for nominal data, for gender data. Instead, you'd use median as the summary statistic that represents the most central aspect of the data. I suspect for some of you, what is confusing are the different kinds of symbols that are used to represent concepts. Mathematics uses both Greek and English letters to symbolize concepts. And when it comes to statistics, there are two sets of symbols. There are symbols that represent the population that you're seeking to study, and then there are symbols that represent the sample statistics from the sample that you've drawn. For example, number of cases. If it is the number of cases that are in the total population, you would signal that with a capital N. If it's the number of cases in the sample that you've taken from the population, that would be signaled with a lowercase n. The mean of the population, if mean is an appropriate measure for this given concept that you're trying to look at, then the Greek letter mu is the signal for population, and an X with a line over the top of it is the mean of the sample that you've drawn. Proportion, small letter p, indicates that it's the symbol for the population. A p with a little hat over it indicates that this is a statistic that's coming from the sample. Deviation from the mean, that would be a sigma with a squared, because that means variance, or a v with a square, which also means variance. Standard deviation from the mean would be the same thing, the sigmas and the s's without the squared. One of the things I want to help clarify is this idea that there's probably zillions of different significance tests out there, and you've got to figure out which ones to use. And I think that in helping you understand the difference between parametric and non-parametric conditions helps us determine what kind of significance test to use. For instance, if the parametric conditions are met, meaning that there's a large enough sample size and there's a decent normal distribution of sample cases, and you have interval or ratio data, then you can use either a z-test for means, which you learned how to do last week, or we can use what's called an f-test if we're doing an ANOVA. And we won't be doing that for another week or so. But just know that parametric conditions, where everything fits what's needed for a parametric test, and we use a z-test or an f-test. If parametric conditions are not fully met, for instance, the sample size is too small, or that we're using proportions instead of means, then we use t-tests of means or t-tests of proportions. And probably the most used measure of significance is the chi-square. And the reason for that is it's used for non-parametric conditions where the sample size is not big enough, or you have nominal or ordinal data, and you're looking at proportions or percentages. And that's what you did when you did the chi-square test this week in your SPSS assignment. Now, one of the things you had to do last week was look at a whole bunch of formulas. And few things intimidate us more than looking at a bunch of formulas that we really don't understand. I want to now present to you the no fear approach to formulas. And why do I say no fear? No fear because we don't have to run those formulas. We don't have to crunch the numbers. SPSS does it for us. All we have to do as analysts is interpret what SPSS is crunching out. So now that begs the question, why did we expose students to such agony of trying to understand those formulas? Here's the reason. Math connects concepts. And equations are simply representations of connections between concepts. So in trying to get your head around those formulas, what we're asking you to do is understand that statistical testing are simply equations that connect means or proportions observed in your sample with the sample size, with the variance in the sample, and with your a priori expectations of what the sample ought to be representing in the population. Having done those equations, you get these critical values, these z's or these t's or these chi-squares, and then the next thing that happens is we connect those critical values, the t's, the z's, or the chi-squares, with the central limit theorem that talks about the sample mean distributions. Let's walk this out for a z-test statistic. Suppose I want to know the average age of MBA students at Bethel. And let's say I'm expecting the average age to be 32 years. The null hypothesis of average age of our MBA students would be 32. The alternative hypothesis would be average age is not 32. And this is a two-tailed situation. Age is ratio data, so the z-test is appropriate. So I go out and I collect data from 30 MBA students and I calculate a sample mean of 35. Now, given the potential variance in the sample and the population of MBA students, given that the age range is from about 22 to somewhere over 60, is 30 a good estimate of the average age of the population? Can you see how the z equation pulls together a number of different concepts? Pulls together the sample mean, the expected mean of the population represented by that mu, the variance in the population, which is represented by the sigma, and the sample size, which is represented by the lowercase n, and then takes them and summarizes their relationship into a number we call the z statistic. And the chi-square test. So how does that work? Remember our gender and minority designation assignment? It's a four-celled relationship. There are two categories of gender, male and female, and two categories of minority designation, white or non-white. So can you see there's four different cells there? If there is no relationship due to minority classification, then we would expect the values in each of the cells to reflect the total population proportions. So there would be about 78% of either gender would be white and 22% of either gender would be non-white. What the chi-square formula does is it connects the observed values in each cell with the expected value in each cell and summarizes the difference. So you see how the formula takes an observed value minus an expected value, does the subtraction, squares it, divides it by the expected value because that's how the relationship works, and then summarizes that across all four cells. And that gives us this chi-square critical value. Now, once we have these critical values, these t critical values or these z critical values or a chi-square value, the next thing that happens is we need to connect it to the idea or the understanding of the central limit theorem. Now you remember from earlier learning that the central limit theorem says that as we take samples, those sample-based measures are going to collect around the center of a distribution of the same measure across many samples. And as it collects, as all these different sample measures collect, they are going to disperse along a normal distribution, this bell curve thing. So underneath this curve, you can imagine that there are all of these different sample measures, whether they're sample measures that are the means that are gathered from the sample, or maybe it's a proportion that's gathered from the sample. So underneath here are a whole bunch of potential sample distribution or sample measures. So central limit theorem says they're going to collect around the true mean or the true proportion of the population. Therefore, we can use probability estimation to assess the trueness of a given sample measure. And that's what critical test values like a t, a z, a chi-square, or an f. They are just sample-specific numbers that indicate where the sample's measure is located under this normal curve. That's all those critical values are. Now, we don't have to calculate those, nor do we have to really look them up on probability tables, because SPSS is going to give us this p-value. Remember, we saw the asymptotic p-value that was spit out from the chi-square formula tables. The p-value is simply indicating the probability that a sample has given us a good estimate of the true value of the population. So the p-value is simply telling us what's the likelihood that that sample measure that you've gotten is either within the major part of the bell curve, shown here in the white part, or it's out in the tails, shown by the shaded part. And you can see that where these shaded parts are lined up right now, it would be a 95% confidence level, saying that if my sample measure is within the white part of this, then I can be 95% confident that my sample measure is close to the actual value of the population. But if it's out in those shaded tails, where half of the probability of 5%, the difference between 100% and 95 is 5, right? So half of it is on one side of the curve and the other half is on the other side of the curve. That's why it says 2.5. 2.5 is on the other side. If my number is out there somewhere, then I can say that no, it's too far away from the expected mean of the population, or the expected proportion of the population. And so I can say that my sample number is not a good representation of the population. Okay, so now we've been talking about these tails. What's up with these tails things? Let me help you understand that. Remember, we're talking about sample measures. And we're trying to determine, is the measure that I got from the sample a good enough estimate of what's really happening in the population? And I can do that because all these different sample measures, if I took a whole bunch of different samples, the measures would all eventually fall under a normal curve, and they would migrate or tend towards the true value of the population. So the tails then are the outside edges of this normal curve. But what's this one-tailed versus two-tailed test? Think of it this way. If you have a null hypothesis that is either an equal to or not equal to, then that null hypothesis is going to require a two-tailed test, because the results can either be higher or lower than the actual. So we'd be looking at a two-tailed test. And our p-value, that 5% probability that we would want given a 95% confidence interval, we would take that probability and we divide it in half. So half of our chance would be on one tail and half would be on the other tail. So 2.5 and 2.5. Added together, that's 5%. If we have a null hypothesis that's framed as greater than or less than, then we need a one-tailed or a directional test. And that means that the results of our sample are either not greater than the actual or it's not lower than the actual. And when we're doing a one-tailed test, what we do is we take all of the probability, all of that 0.05, and we put it on one side of the bell curve. So if it's greater than, then we would put all of that 5% probability on one side of the curve. If it's lower than, we'd put all of that 5% on the other side of the curve. I know all these concepts can be very confusing, and I understand that it takes some time to get our heads around it. Here, how about a little transparency? When I did my MBA way back when, I actually did it in multivariate statistics. So I understood this stuff really, really, really well a long time ago, and I actually could hand crank all of these equations. But I haven't taught this class for 5 years. So one of the things I've had to do in the last month is I've had to go back to the videos. I've had to go back to some of my other resources and reschool myself on all of these concepts because they're not really intuitive. I mean, eventually they become intuitive, but they aren't at first glance. And so if I was having to revisit things to understand them so that I could explain them to you, I can't imagine what it's like for some of you who really don't have a lot of experience with statistics. So given that, I want you to know that I am very available to ask questions. You can contact me to set up a phone conversation so that we can converse about these things. I'm there to help you make sure you understand this. So please take me up on any opportunity that you might require of me to give you some extra help on this. Thanks for listening to this. I hope that I cleared up some things, and I look forward to helping you along in the next step on this journey.